Well, hello, welcome again to Maths 5. This is the fourth recording for Chapter 3 on continuity of functions. And we finished off last time looking at this rather bizarre example of this function called the ruler function, which is -1 if x is irrational and 1 if x is irrational, and we gave a little proof there that this function wasn't continuous anywhere by using this definition up here. Now I'm going to, we really still want to try and deal with this function that whose graph I put up before, and that's this one. F of x is sine 1 on x. What the hell is this doing near 0? The picture would indicate that the function's going totally bizarre, totally crazy, near x is 0. The computer can't really draw what's happening there. It seems to be zipping up and down, and it's probably clear that this is not going to make any sense as x goes to 0, but we need a proof of that. It's not clear what on earth's happening inside this funny area in here. And so we're going to deal with this particular function in a moment. But to do that, we need a little theorem. And I'm going to state the theorem, and I'll say something about it, but we'll probably skip the proof. I've included the proof there. It's very technical, and you can read through it if you like, but I won't go through it formally here. So what this theorem says is you've got f as a function on some domain, and you pick some number in the domain. Well, it says that f is continuous if and only if the limit of f of xn, so you take some sequence of numbers, you take a sequence now, and you evaluate f at each point in the sequence, and then you take a limit as n goes to infinity, and if that sequence tends to the point x naught, then f will be continuous, means that the limit of f of the sequence is f of the limit. That is, you can take f of both sides of this, and f of xn goes to f of 0. And this is true if and only if this is true. So the result says then that if f is continuous, and we have a sequence xn which goes to x naught, then f of xn goes to f of x naught. That is, continuity preserves convergence. Now that's a very nice theorem and a nice result. Very nice theorem and a nice result. Now I'm not going to go through the proof with you here. I've written it all out there. You can read through it if you like. It's a fairly technical proof, and so I'll leave you to go through that if you're interested in that. More to the point, I want to show you how to use this result. We're going to use this result finally to analyze this function f of x is sine 1 on x, which we've mentioned before. F of x is sine 1 on x. So here's our example. We're going to look at this function sine 1 on x, and I'm going to show that it cannot be made continuous at x is naught. In other words, the limit of this thing as x goes to 0 does not exist. And so what I'm going to do is I'm going to construct a sequence, and here's the sequence. I'm going to take the sequence xn is 2 over n pi, where n is 1, 2, and so on. So x1 would be 2 over pi, x2 would be 1 over pi, x3 would be 2 over 3 pi, and so on. Now it's pretty clear that this sequence tends to 0 as n gets very big. On the other hand, if I work out f of xn, so I'll work out here f of xn, well, that's going to be the sine of 1 over xn. Now that's the xn is 2 on n pi, so this is going to be the sine n pi on 2. And now what's this doing? Well, if n is 1, I get the sine of, so it actually starts out at 1. Sine of pi on 2 is 1. If n is 2, then I get the sine of pi, which is 0. So in fact, what I should have done was just to rub this out here. So it's starting out at 1, and then if n is 2, you get 0. If n is 3, sine of 3 pi and 2 is minus 1. Then it'll be back to 0, and then 1, and then minus 1. So this sequence we get of the f's of this does not converge. In other words, this goes to 0, but f of this does not have a limit. That is, xn goes to 0, but f of xn does not converge. And our theorem says, well then, that means the function we started with is not continuous. So this tells us that this limit, x goes to 0 of sine 1 on x, does not exist. And so as we saw in that funny diagram that I got the computer to try and draw it, crazy things happen as you go towards 0. And we've just proven here that the function's not continuous. It doesn't have any limit. This limit doesn't make any sense as x goes to 0. Well, we've defined what we mean by a function being continuous at a point, and now I'm simply going to extend this a little bit to an interval. So we say that a function is said to be continuous on some interval a if f is continuous at each point in a. And a function is called continuous if it's continuous on its domain. So it immediately follows that if f and g are continuous, then so is f plus g. We can add two continuous functions, the answer is continuous. Subtract two continuous functions, the answer is continuous. Multiply two continuous functions, the answer is continuous. We can divide, provided we don't divide by 0. And we can also take the composition of two functions, f circle g, that is f of, so that's another way of saying f of g of x. We can take the composition. So, very simple example of what we do here. So we're going to just explain why this complicated looking function is continuous everywhere except at these 2 points. Now the function looks complicated, but in fact the solution is not complicated. The solution is very simple. I'm just going to say that we know that x is continuous. We've proven sine x is continuous. So that means the product of these two is continuous. So that term there is continuous. X minus 2 is continuous. So is its square. So this term up here is continuous. X squared minus 4 is continuous. So when I divide the two, it's going to be continuous. So f is continuous, except when we're dividing by 0, except when the bottom is 0. That's when x squared minus 4 is 0. And that occurs when x is 2 or minus 2. So using this algebra of continuous functions, we can say once I build up something complicated out of simple functions that we know are continuous, then the result we get is going to be continuous except when we divide by 0. And that happened in this case at these 2 particular points. Well, we're going to discuss, just to finish off with, some different types of discontinuity, different types of points where the function fails to be continuous. So we say firstly that f has a removable discontinuity at x0 if, when we take a limit of the function, this exists, but it may not equal to f of x0, or f of x0 doesn't exist, isn't defined. So, for example, if we take this function here, we're going to consider this function here, and we're going to show that this function is not continuous at 0. However, the discontinuity is a removable discontinuity. That is, I can redefine the function to make it continuous. Here's the solution of this. It's fairly straightforward. So I've got sine x on x is not 0, and 2 when x is 0. So again, we're going to take a limit as x goes to 0 of f of x. So that's the limit as x goes to 0 of sine x on x. Now we proved that limit, we've proved before that limit is 1. So, but however, the way this was defined, f of 0 was not 1, it was 2. So f has a discontinuity at x equals 0, but it is removable. It is removable. Because what I can simply do is, I could redefine f of 0 to be 1. So I could simply go back and say, well, let's get rid of that 2 and replace it with a 1, and now it's continuous. So the function we were given is discontinuous at 0. The limit it exists but doesn't equal the value of the function. On the other hand, it is removable. And that's what we mean by removable discontinuity. So as I said here in the note here, that by replacing 2 with 1, we can make the function continuous. The second type of discontinuity is what we call a jump discontinuity at x naught. That means that if you take a right-hand limit, if you approach x naught from above, then that limit exists. And if you approach x naught from below, then that limit exists, but they're not equal to each other. And the example of that is, we've seen this one earlier, f of x is x on the absolute value of x at x is 0. And we saw that had a jump discontinuity. Again, here's the analysis of this. So we've looked at this example before, but if we take a limit as x goes to 0 from the positive side of f of x, then we just get x over x, limit is 1. If we take a limit as x goes to 0 from below, then as we saw before, absolute value of x is minus x, so this gives me the limit minus 1. Both of these limits exist, but they're not equal. And so we say that f has a jump discontinuity at x is 0. And of course, as I mentioned before, graphically it's looking like this. We've got a hole at 0 at this one both ends. So x is 1 if there. So this is f, this is x. And then it looks like minus 1 on this side. So it comes along, it's perfectly continuous, and then suddenly it jumps up to here. So you can't fill in the gap. This is what's called a jump discontinuity. Other examples of this would be something like, for example, f of x is 1 over x. This at x naught equals 0, this has an infinite discontinuity. So this is neither a jump nor is it removable. So this is sort of a third kind, if you like. So we say that f has a discontinuity of the third type if x has a discontinuity at x which is neither of the above two. So if it's not removable and it's not a jump discontinuity, then it's just, well, it's one of the third type. So obviously this one's not going to work here, because if you try and take the limit as x goes to 0 of 1 over x does not exist. And in fact, if you go from above, it doesn't exist. And if you try and go from below, it doesn't exist. Does not exist. And so it's neither of the above. It's not removable, it's not a jump discontinuity, it's an infinite discontinuity. And of course, you know from the diagram, from the picture, as you go towards 0, this way it's zipping up to infinity, this way it's zipping down to minus infinity. And this is known as an infinite discontinuity. Well, final comment here, final example of one of these. This is this sine 1 on x that we looked at before. This is f of x is sine 1 on x if x is 0, and I'm going to make it 0 if x is 0. And we say that this has an oscillating discontinuity at x is 0. Because as I showed you before in the diagram of this, in the graph of this function, as you go towards 0, either way, the function is zipping up and down. It's not an infinite discontinuity. There's no left limit, there's no right limit, but it is bounded. It's not a jump discontinuity. It's an oscillating continuity. So what I did there was I defined the function to be 0 at the origin. So we do have a discontinuity. It's defined for all x, but we have a discontinuity at x equals 0, which is what we call an oscillatory discontinuity. And we'll have a look in the tutorials at various different examples of different types of discontinuities. So this is a slightly shorter video because the previous one was a bit longer, so this one's not quite so long, and I'll finish it there. So have a look at the tutorial problems. You'll see that although we've done some moderately heavy theory in this chapter, the sorts of things that I expect you to be able to do, you'll see from the tutorial problems, they're not quite so hard.